it's a pleasure to present for you. It's a topic of great interest, and I'm very enthusiastic about this particular topic, so I appreciate the opportunity. I'd just start with a couple of examples of geosynthetics in Australia, which are one in Australia. This one here is quite interesting and innovative. It's an off-grid farming solution. This is a tomato farm using with these large glass houses here to grow tomatoes. It's located in a remote area on the coast. It's completely off-grid. It generates its own power from the solar field. Takes seawater to irrigate the tomatoes and has to clean the seawater in an RO plant. And geosynthetics are used to store the seawater coming in, the processed water that's clean, the effluent water before it's pumped back out into the ocean. Just an interesting project. And another example here, this is of floating cover technology. This is a project we did in the Marshall Islands, the capital Marjaro. The only source of fresh water on the island is from the runway. When it rains, they harvest water from the runway, and they clean the water and they store the water in these storages here. You can see the runway is up here, and these are the covered storages with the clean water in. Another relatively innovative example of floating cover technology. Floating covers can be used in tanks. Here's an example from a project in South Africa near Cape Town, supplied to me by our friends at Aquatam. And today I'm going to talk to you about floating covers. I'm going to talk about the life cycle and replacement cycles for floating covers, and then illustrate those concepts with some case studies. Floating covers they're barriers that float on a liquid, usually in an earthen basin. The earthen basin is usually lined as well. Other than the earthen basin, they require limited infrastructure compared with alternatives. They can be almost completely sealed, and they generally provide a low-cost containment solution compared with alternatives. The example in the top here. That's an asset that we built a couple of years ago now. It's a liquid fertilizer storage. Two basins were built, line the cover basins, so they've got some redundancy. They can take one basin offline. And that asset was built in around about half the time and a third the cost of the alternative technology, which in this case was glass-coated steel tanks. So substantial benefit. And the applications mostly that we use floating covers in are sustainability applications, evaporation control, renewable energy, significant demand in harvesting methane, but also uses which is then not only flared to reduce CO2, to reduce methane, but also as an energy source, pumping that gas into engines, and thermal batteries, and I'll talk about those a little bit later. Odor control is an important use also, as is stopping contaminants getting into the storage, such as rain increasing inventory, solid contaminants, or even just controlling the temperature of the storage. Two or three examples. I mean, they are around the world. So the example on the left is from Israel. Israel, most of their water comes from bore water that's treated in RO plants. And it's almost all stored in earthen basins, lined and covered earthen basins. Interesting that I have this example from Spain, adjacent to where you are. High evaporation rates are used to store water to irrigate an olive farm. Very simple, relatively inexpensive design solution. I'll talk about this later, but this has got a central plate. These features here create a central plate. Design in that particular asset was built in polyethylene materials. So unlike a lining systems generally are covered. a lot of the research available within industry and academia is around those covered applications. There's less experience in terms of exposed and UV aged geomembrane solutions, and also covered liners are generally at lower temperatures, whereas covers are the opposite. Cover systems, they're often in challenging environments, high temperature environments, because they're being used to control evaporation, as an example. They're seeing high temperatures and high UV loading. Where inventory management is an issue, water inventory management is an issue in Australia. They're in tropical, high rainfall, cyclonic environments. And so they're much more challenged than a conventional lining system is. Picture on the diagrams on the right show you where it's hot around the world, and the kind of ranking in terms of UV being damaging for geomembranes. Generally, the Middle East, Africa is the worst, the highest loading. Australia is a close second. North America and Europe would be kind of third in terms of that UV loading. And it is important because we find that the correlation between UV lab aging tests and real life experience is not completely reliable. So the point I'd make is that having service experience when selecting geomembranes is quite important. The other aspect of floating covers and materials is that they get two-sided aging. So on the one side, they're seeing high temperatures and UV. On the other side, they're seeing the contained liquids. Very often in geomembrane solutions, they've got the contained liquid on one side and a relatively unchallenging other side because it's against some kind of earthen storage or GCL or something. And the contained liquids vary significantly across the range of applications that we build. Irrigation water is pretty benign. It's not challenging to the geomembranes at all. And at the other end of the scale, we're covering potable water storages where the chlorine in the water is quite challenging. RO plants with low Langley saturation, low LSI levels, very, very challenging. Anaerobic reactors, this is an example of doing material testing to prove its performance, and this is in a highly concentrated version of an anaerobic reactor liquor to prove the material's performance. Another thing covers need to do is to flex. When I show some examples of how they're designed, you'll see why this is important. Most membranes aren't used in a flexing environment, but for a floating cover they are. It's a key design issue. The amount of flexing, the extent and the frequency of the flexing is really important. And the flexing does degrade over time the geomembrane performance, as you can see from the example data below. And you can see in the pictures here, this was a flex test which was undertaken to validate a material, and you can see the initial live failure here. You can see cracking in the resin, and eventually complete failure of the resin. So I mentioned they're used in a number of different applications. Potable water applications, there's a number of benefits for a floating cover. Evaporation control. Potable water is very expensive water, so you want to minimize how much you lose through evaporation. It keeps the temperatures in the storage stable. It makes it much easier to manage the water quality when you've got stable water temperatures, when you're stopping the UV loading into the water, and it eliminates contamination getting into this critical water supply. Wastewater solutions often have an emissions reduction issue that's important. Odor control. Where I'm based in South Australia, we're surrounded by wineries. All the wineries have effluent has terrible odors. They will have odor control systems on their processing plants. And often it's important to keep the rainwater out of the storages that would otherwise increase the wastewater inventory that then has to be treated or processed. And then anaerobic reactors, so harvesting gas, maintaining the temperature inside the reactor for stability, and also gas storage, and I'll talk about that as well a little bit later on. Here's an example of an anaerobic reactor. This is the cover over the reactor here. That the cover is slightly inflated, and in this particular example, this is one of the largest meat processing facilities in Australia. And in this example, they reduced their carbon emissions from that facility by almost 90%, and they saved $1 million a year on their energy bills. So a hugely beneficial project. So we can divide floating covers into two generic types: covers that are generally static and covers that need to be dynamic. So if we start with static covers that are at a constant water level, there's no need to manage change in material area. They do need ballasting. They need to have some kind of system that creates an appropriate level of tension in the geomembrane. They need to have features that allow water to be collected in a controlled way to exit points, and they need to be stable under wind load conditions. They typically can be positive or negative pressure operation, or more often these days bimodal, where they operate in both positive and negative pressure modes. You can see the example here, where this is quite commonplace in Asia, where very simple covers are constructed that are permanently inflated with some pressure. Relatively short life, but a very cost-efficient way of creating gas harvesting and gas storage. Anchoring can be by an earthen trench or a concrete beam. The environment under the cover typically with these assets is pretty aggressive. There's usually acids, particularly hydrocarbons, oils, greases that are pretty damaging. That was the picture earlier of the immersion test that was assessing fogs. To construct these static level covers, it's necessary to have water in the storage at the level similar to the intended operating level for the storage. For smaller storages, the covers are fabricated on site at the construction site adjacent to the lagoon, and then deployed over the lagoon, as you can see in this example here, and this small example here. To give a sense of scale, we've just finished constructing a storage like this, and the area was 25,000 square meters, which is about as big as you can manage to deploy by this technique. When you become bigger than that, this example here, which is a very large anaerobic reactor cover, you need to build work platforms and can create a work platform within the water and construct on top of the water on that work platform and deploy into the water. For these kind of lagoons also, there's some particular safety issues that can be troubling. If they're active storages, they're usually producing hydrogen sulfide, which of course is in a higher concentration, which is lethal. And they're also producing methane, so there can be some quite significant issues to deal with around health and safety and ensuring a safe working environment. Covers that need to have a fluctuating water level, the design's quite different. So if you look at the top diagram here, they're pretty much always constructed when the storage is empty. as water is put into the storage, you can see in the middle diagram here, imagine that's water now being introduced between the liner and the cover. The area of geomembrane in the cover is now greater than the area that it's sitting on. And so this is where we have these ballasting systems, these weight systems in here that pull the material into that trough and maintain a nice taut, smooth cover without wrinkling in areas that we don't want wrinkling. And the large picture here, you can see here's the ballast line here. We've got float systems either side, and the surface of the cover is smooth and flat and exactly as design intended. And that's a really, really good photograph of a well-designed and well-constructed floating cover. To create that tension, there's a couple of ways that can be done. This example here is what is usually known as a Y system. So there's a kind of a Y shape here, and there's similarly at the other side of the lagoon, there's another Y shape here with ballast and floats. The alternative, we saw that in the example of that Spanish cover, is to have a ballasting system around the periphery of the storage. And there are various reasons why you might use one or the other. These ballasting systems also provide surface water management, so that any surface water is collected in these ballast lines, and here's a pump system to extract that water. I mentioned anchoring. Here's an example of an earthen anchor, of a concrete anchor with a battening system to secure, or earthen anchors can be used. Rainwater management. Here's some bit more detail, and you can see now the way the troughs are working. This photograph's taken during commissioning of the asset, so it's been deliberately overfilled with water in the troughs. Normally they'd be quite small. Inside this extraction system, there's a screen to stop debris getting in. Here's the suction outlet. In this case, the pumping system is off cover. It's a suction system that's sitting on the crest. You can also have pumping systems on the cover, and we've got some uncomplicated float system with sensors to detect water levels to turn the pumps on, turn the pumps off. Quite a lot of the assets, most assets, the owners want the ability to go inside to do inspections or repairs during the life of the asset. So here's an example of a hatch. The hatch is designed. It's got a sampling feature within it. It's designed to allow a fully suited diver, to easily enter the storage. It's sitting on a foam work platform that deliberately has the buoyancy to allow a diver and his diving mate to stand there stably and safely. And you can see here anti-slip walkway materials. So in Australia, there's quite a significant focus around safety with these assets. A lot of the specialty applications, the specialist materials that are used are only produced in relatively narrow roll widths. They can be as small as 1.2, more typically 2.4 meters wide rolls, unlike polyethylenes at 7 or 8 meters. And so for a couple of reasons, it's favorable to prefabricate. So for those kind of applications, we bring materials into our dedicated prefabrication facility here, and we prefabricate the panels in an environment that's clean, temperature controlled, high quality weld seams, minimize the amount of welding that's undertaken on site. And we can create quite large panels and reduce the construction durations on site by doing that. Typical construction of these dynamic covers. So this, if you look here, you can see the black. The black is the lining system. Then this is the cover system being installed. You can see here these are all the ancillaries being fitted to the cover for all the float systems and the ballast tubes and so forth. The construction durations of the covers are 3 or 4 times longer than building a lining system because of all this extra work that has to be done. Commissioning can be quite important. This is a potable water asset. So once the asset's been built, there's usually a need to do chlorine cleaning to get any residual out of the system, make sure it's suitable to take the proper potable water. And most of the cover systems that we build have quite strict controls around seepage, lining seepage. So most of the projects we would have a conductive system, conductive layer beneath the primary liner to allow us to do electrical surveys on the liner before the cover is installed. To talk about life, here's some examples of materials failing. There's some weld failing here. This is a seam failure in here. This is just the materials failed. The number of things the important factors to maximize the life. Long life assets would be in the order of 40 years. Not a bit more maybe, but we haven't gone past 40 years yet. Short life assets can be 5 or even 10 years, depending on the design requirements. Often when designing for these kind of applications, there's very little reference data to turn to. There's very few technical papers or standards that can be used. It's based on either specialist knowledge to work out what materials to select. The material selection is absolutely critical to the life of the asset. Unlike a lining system, it is permanently loaded. Very often we'll be using reinforced materials. It's got this double-sided degradation mechanism, UV and temperature above and chemical attack below, and it's being flexed and folded all the time. Design's equally important. The features I've spoken about are necessary for the cover to function, but the way those designs are created is really critical to not generate stress concentration points in the material, and that's quite important and challenging issue from design. Construction needs to be good because it's permanently loaded. Any construction weaknesses will be more readily exposed during the life of the asset, and really importantly, they should be operated within the design parameters, and clients often aren't too sure what those operating parameters are and don't necessarily follow them. This is a real live example here of a floating cover that failed. The client didn't undertake life assessments, just waited until eventually the liner ripped open. Where the black marks are is where a dive team had to go in and make repairs to make the asset operational again until it could be taken offline to be permanently repaired. Maintenance is really, really important. Not done too well. Several examples. So maintenance includes going inside, inspecting inside. You can see the pictures on the right-hand side there. Divers going inside. These days we've got robotics that we use to go inside covers. We put them to the hatches, and we can do a visual inspection. We can get a location survey of where we've inspected, and we can also do electronic surveys underwater, under the cover these days as well. You can see here in the middle examples of assets that haven't been maintained too well. There's trees growing in the ballast lines, and here rushes and so forth. Lack of maintenance does shorten the life. Proper maintenance does extend the life. Residual life. So there's a relatively reliable way of predicting the life in geomembranes. Most have probably seen the classical aging model of geomembranes, a period of time here where the membrane's performing well. It's doing what it's supposed to do. The additives within the resin are performing well and protecting the base resin. It goes through a phase when it starts to degrade, but then it goes into the rapid degradation period. In this early phase, we'll use what we call multi-parameter assessments. We don't rely on any one test to assess how the material is performing. In this example on the right, there's 10 different tests have been performed, and we're looking for several of those indicators to be showing us that there's an issue with the material. Once we get more towards this third phase, C here, you can just focus in on monitoring the most critical properties of the material. Here's an example where in this particular case, the best indicator of the life was actually exposed flexing failure. So in terms of life, good design, good material selection and construction, maintain it well. It is possible to quite reliably predict the life of the asset, monitor it during its life, and predict when it needs to be maintained, and avoid this situation. This is a real example of where that wasn't undertaken on this particular asset. The material became degraded. The owner didn't know. You get one significant weather event, and the material catastrophically failed. So that's the general introduction. So some case studies. I'm sure it's the same in Europe. Bioenergy is an area of focus in terms of renewables. In Australia, there's a significant focus. I think Australia is probably lagging where you are in Europe. There have been a number of studies showing how important it is to cut the emission of methane. There's a commitment from the COP26 summit to reduce emissions by 30%, and that plays straight to gas harvesting, anaerobic reactors, gas harvesting, which avoids odor issues. It avoids the CO2 being emitted into the environment, and you can pump that gas energy into gas engines. This is another example where the asset wasn't adequately monitored towards the end of its life and had a catastrophic failure, as you can see. And the material selection wasn't entirely appropriate for the design expectations that the client had for the asset. And for that reason, we did, in this case, we did some significant materials testing to confirm that the selected material for the new design would be durable, because the client had a poor experience with the original build. So this is the rebuilt cover in this picture here. The cover area is 50,000 square meters. The design requirement is it's a large area, so it's going to resist wind loads when inflated under positive pressure. It's a bimodal cover, I mentioned, so it normally operates as a negative pressure cover, so it sits flat on the water, but it can operate temporarily as a positive pressure cover to provide a gas storage so that they can maintain all the gas plant and equipment. It needs to have arteries to allow the gas, because it's a large area, to allow the gas to escape to the periphery. So around in this design here, around the periphery of the storage is a gas ring main effectively, and there are pathways to allow the gas out from the middle out to that gas main to be extracted. The client wanted a minimum 20-year life. We had to make sure we had suitable UV, not overly difficult with quality geomembranes these days. Chemical attack, the materials in this storage are particularly aggressive, so that was really important. And particularly, the most damaging element of the chemical attack was hydrogen sulfate gas and liquid. Um, um, so in terms of selecting materials, the, um, the gold standard would have been something like CSPE or ethylene interpolymer alloy. These materials are relatively more expensive than polyethylenes. The flexible polypropylene, not recommended. That's what was previously used. It's got poor performance generally. And the material in the end that was chosen to be suitable, so not the best, but a good value proposition for the client, giving adequate life, meeting the design requirements, was HDPE. So we wanted to demonstrate that there was no risk to early failure of the material. I guess most people in your chat would be familiar with this aging model, this classical aging model for polypropylene materials. So to demonstrate this, we couldn't test the material for years and years. We only had a limited amount of time. So we did an immersion test. We did the immersion test at elevated temperature. We very significantly concentrated the liquors that we tested into much higher concentrations. And we also tested thin film materials as well as the intended production material. And from all those testing, here's some of the results here. One of the key indicators we were looking at was stress crack performance of the geomembrane when exposed to this accelerated test. And also for the thin film, we were particularly looking at the additive package durability. And from all these tests, we were able to demonstrate that we were seeing additive package retention past 20 years design life. So we had not only had we retained the additive package, we still had the material could start to degrade before it became unserviceable. So we had plenty of safety factor. And that the stress crack performance equally was extrapolating to be well past a 20-year life. To build it, the concrete beam that it was originally built on the inside had been severely damaged by the hydrogen sulfide. We needed to minimize the cover off time because when the cover's off, we had issues around odor and smell for the local residents. So we actually built a new anchor beam on the outside of the existing anchor beam, so we could build that before we took the cover off. We had to remove you have to use plant to get it's tons and tons of material to remove. And once we'd got the cover off, of course, these things accumulate a lot of scum over time. So the lagoon was full of solids. So we had to put barges in to remove all the scum and build a drying bed to put all that solid material and get rid of it. And then for construction, I mentioned before the need on large assets to build in the lagoon. So here you can see we had to design and certify a marine work platform. We had to install that platform into the lagoon, and then you can see here that we were able to then fabricate the geomembrane on the work platform and then deploy into the lagoon. We had additional challenges as well because we're working on a live asset. It was not possible to reduce the gas emissions. We had to have all sorts of extraction systems along the work front here. We had to have extraction to extract the methane away from the welding process and so forth. And the whole site was covered with gas alarms in case there was an issue. And that's the completed asset. Quickly on to thermal storage. In Australia, there's companies that are developing renewable solutions, solar-based renewable solutions using water as a thermal battery. This is an asset. This here is an asset that's been built in Victoria in Australia. It's an operational prototype prior to building a large-scale asset. And the way it works is that generate hot water. Hot water's discharged through a Rankine cycle engine to generate the power, and the cold water goes back into a storage. One storage is hot, one is cold, and the cold water is used to cool the radiation towers. And that allows them to have renewable energy that's dispatchable, not when the sun's shining, but when the power is required. So we needed two pits. You can see the example of the pit here. The pits have diffusers inside them so that they can manage the water flows and the temperature flows within the storage very, very carefully. They require a high level of thermal insulation. The water in the hot pit particularly is very challenging at 95 degrees at the top of the storage and 70 degrees at the bottom. It's a big challenge in that space. We're doing some work with Catherine on those materials. The requirements were 90 degrees C, 20-year life. Normally, HDP is limited to around about 60 degrees C. There's a couple of places to go to for a high temperature performance. PERT resins, polyethylene raised temperature resins, are a particular category, and also bimodal resins that have a modified production process that allows it to kind of design a crystalline structure to be created. Here's an example of this green line, an example of one of these high temperature resin formulations that's demonstrating much higher levels of performance at elevated temperatures. We've got a very complicated floating cover. This topic's about covers, a very complicated floating cover in this case. We had to keep the cover very, very close to the diffuser inside the storage, which meant we had to manage all the water flows on the surface of the cover with only very, very small gradients. We had a stiff cover. We had to model all this quite carefully. We built scale models to validate the calculations, and then manage the stormwater management on top of the cover and water management inside the cover. The temperatures are sufficiently high that we get diffusion through the geomembranes, and therefore we're going to manage water inside the cover. And that's the asset. This pit here is the hot pit. This is the cold pit. You can see the cover system and the ballasting system that's managing carefully those waters on top and inside the cover. And lastly, a large potable water asset. This is the largest floating cover in the Southern Hemisphere. You can see over here is Sydney, the Opera House and so forth. This is actually the floating cover. You can get a sense of the size of the floating cover. It's huge, very large asset. You saw this picture before. This is an asset that wasn't the asset replacement cycle wasn't managed too well, and they had a catastrophic failure that had to be repaired by divers to keep the asset serviceable until it could be replaced. The asset is actually built in two elements, so we're able to take one element offline, continue to service Sydney with potable water, while the other one is being refurbished. There was extensive candidate material testing. The original asset lasted 18 years thereabouts. In the 18 years since that was built, there's been a lot of material developments. The Sydney Water, the asset owner, not a technical expert, and they were insistent on doing extensive testing, which is commonplace in Australia now, extensive testing to demonstrate which are the most appropriate materials. A number of materials were assessed, and out of all those materials, two were judged to be suitable in these kind of applications. And as it happens in this particular case, we built it during COVID, and because of COVID, we built the liner out of one of the materials and the cover out of the other material, so that we had some flexibility in case COVID shut one of the factories down as a risk mitigation strategy. Here's the cover here's the system being built. You can see now that you have there's an inner reservoir and an outer reservoir effectively. This tan is the cover being installed. This grey is the liner being installed. We're concurrently installing all layers. This here, in fact, sorry, and this is the conductive geotextile, is this black here. Prefabricated again, I mentioned, so this particular tan material is only 1.2 meters wide, so all the materials were prefabricated. The asset had some construction challenges. About a third of the walls were vertical walls, as you can see here. This black again is the conductive geotextile that we're using to make sure we can do electrical surveys on the finished liner. This exposed concrete wall here had terrible groundwater seepage issues. We had to refurbish that whole wall before we could then finish relining. Good example of safety. So here, here's a foam walkway from the crest out to a diver's access hatch. You can see the large foam features to provide stability, anti-slip features, different colors so that the walkway is clearly identifiable. The anti-slip walkway is narrower than the foam section to again help with stability. Again, you can see well designed, well constructed. The ballast lines are straight, the cover tensions neat. Exactly, precision engineering effectively. And I think I've just about managed to do that within a few minutes of the allotted time.